Hello, in this video I'll be working through Unit 4 homework problems 9 through 13. These problems all have to do with related rates. Number 9, a sailboat is sitting at rest near its dock. A rope attached to the bow of the boat is drawn in over a pulley that stands on a post on the end of the dock that is 5 feet higher than the bow. If the rope is being pulled in at a rate of 2 feet per second, how fast is the boat approaching the dock when the length of rope from bow to pulley is 13 feet? So the first thing we should do is draw a picture and label our constant values and label our unknown values. So I'm just going to draw a picture of a boat in the water. Here's my boat in the water, and it's approaching a dock. So we have a dock over here, and there's a pulley on the dock, on a pole on the dock, and it has a rope attached to the bow of the boat. And so it's moving, the rope is pulling the boat in. So the boat is moving in this direction. And this is just sitting on the dock here. Now we're told, let's read through this again. So the sailboat is at rest near the dock. A rope attached to the bow is drawn in over a pulley that stands on a post on the end of the dock 5 feet higher than the bow. So this distance from the pulley to the bottom of the deck is 5 feet. I'll go ahead and put units on that. The rope is being pulled in at a rate of 2 feet per second, and we want to know how fast is the boat approaching the dock. So we're going to create a right triangle here, where we have this one leg, a constant height of 5 feet. And we're interested in the length of this leg and the length of the hypotenuse of that triangle. So I'll call the leg X and the hypotenuse Z. So we've drawn our picture, we've labeled our variables and our constants, and now we want to identify what is the rate that was given and what is the rate that we're trying to find. So step 2, we found our picture, or step 1, we drew up and labeled our picture. Step 2, we're going to identify the rate that we're given. So it says the rope is being pulled in at a rate of 2 feet per second. That's referring to Z, the rate of change of Z with respect to time. So that would be dz dt. dz dt is 2 feet per second. But since the rope is drawing the boat in, the length of z is actually getting shorter as the boat is approaching the dock. So it's negative 2 feet per second. That's the rate that we're given. We're asked to find how fast is the boat approaching the dock when the length of the rope from bow to pulley is 13 feet. So we want to find dx dt, the change in x with respect to time. And we want to find that rate at the specific instant when z is 13. So I highly recommend you write down the rate that you're given and the rate that you're trying to find. That's going to help us in step 3, where we have to come up with an equation that relates our variables. So the variables of interest are the variable z and x. That comes from the rate we're given and the rate we're trying to find. Z and x. So I need to try and write an equation that relates z and x. So what equation can we come up with that has a z and an x in it? Well, we do have a right triangle. X is a leg, z is a hypotenuse, and we know the other leg is a constant value of 5. So we can use Pythagorean Theorem to write an equation: x squared plus 5 squared equals z squared, right? Leg squared plus leg squared equals hypotenuse squared in a right triangle. So here's our equation that relates x and z. Next, we're going to differentiate our equation with respect to time. So left to right, implicit differentiation. We take the derivative with respect to t. The derivative of x squared is 2x if we're taking the derivative with respect to x. But since we're taking the derivative with respect to time, we need to compensate for the change in variable. So chain rule tells us that we need to multiply this now by dx dt. So that'll convert the derivative with respect to x into a derivative with respect to t. Plus the derivative of 25. Well, the derivative of 25 is 0 with respect to any variable. so we don't have to write the plus 0, you can if you like, equals, and then the derivative of z squared. The derivative of z squared is 2z if we're taking the derivative with respect to z, but we're not. We're taking the derivative with respect to t. So to compensate for that change in variable, we're going to multiply by dz dt. Okay, so that was step 4. We've taken the derivative of our equation using implicit differentiation. And now we're going to substitute in all of our known values and solve for our unknown. Our unknown that we're looking for is the dx dt. So we should be able to substitute in values for everything else besides the dx dt. So the first thing I need to substitute in for is x. Well, what is x? We still need to find it. We know that we're looking for the derivative at one specific moment in time. That's when z equals 13. So at the moment in time when z equals 13, this becomes a right triangle with leg 5 and hypotenuse 13. Using the Pythagorean theorem, then, we can figure out the value of x at that moment in time. When z is 13 and the height is 5 feet, then x equals 12. Okay, and again, that just comes from Pythagorean theorem down here. We'd have x squared plus 25 equals 13 squared. 13 squared is 169. We subtract 25 on both sides, we get x equals 144. Or x squared equals 144. We take the square root, we get x equals plus or minus 12, but we know x can't be negative 12. That wouldn't make sense in the context of our problem. So x is 12. At this moment in time, x is not always 12, but at the instant when z is 13, x is 12. So now let's go back to substituting in values. So now I know at the moment in time in question, x is 12. So 2 times 12 times dx dt equals 2 times z, and at this moment in time, z is 13, times dz dt. But at this moment in time, we know dz dt is negative 2. So now we just have to solve for dx dt. So dx dt at this moment in time, and if I want to be really specific with my notation, I can say dx dt at z equals 13, right? That's what we're looking for over here. That's what we're trying to find at this moment in time is 2 times 13 times negative 2 divided by 2 times 12. So my 2's will cancel out, and this 2 and this 12, 2 over 12 reduces to 1 over 6. So I have negative 13 over 6. Now we still need to think about our units. The rate that we are finding is dx dt. So the units for x is this length right here, the distance from the bow to the dock. That's measured in feet. And the t, my time, is measured in seconds. So my units are going to be feet per second. Negative 13 over 6 feet per second. Number 10, a baseball diamond is a square with sides 90 feet long. Suppose a baseball player is advancing from second to third base at the rate of 24 feet per second, and an umpire is standing on home plate. Let theta be the angle between the third baseline and the line of sight from the umpire to the runner. How fast is theta changing when the runner is 30 feet from third base? So step 1, we're going to draw a sketch and label our constant values, label our unknown values. So we have a baseball diamond. I'm going to draw that as a square. Each of these sides are 90 feet, so I'll label that in a moment. We also know that the baseball player is running from second to third base. So second base is this corner up here. Third base is this corner over here. And so our runner is somewhere in between second and third. I'm just going to arbitrarily place him right here, just for a point of reference. Theta is the angle between the third baseline and the line of sight from the umpire to the runner. So the umpire is at home plate. He's down here. And the line of sight from the umpire to the runner is right here. Okay, I missed my mark a little bit. That's a little better. So we have a right triangle, and we're going to label this side Z, the hypotenuse in our right triangle. we know that this side now is 90 feet, and that's a constant value. That's not going to change. The length of the third baseline is not going to change. It's going to stay 90 feet. What is going to change is the distance from the runner to third base. As time goes on, he's getting closer and closer to third. So let's call that variable x. Okay, we've labeled our constant and our variables. Let's move on to step 2, where we identify the rate that we're given and the rate that we're trying to find. So we're told that the baseball player is running at a rate of 24 feet per second. And the baseball player's distance from his position to third base is represented in our picture as x. So that rate is dx dt. That's how quickly the distance x is changing with respect to time. And as the runner approaches third base, x is actually getting smaller and smaller and smaller. So this rate is going to be negative 24 feet per second. Now the rate we're asked to find, we want to know how fast is theta changing when the runner is 30 feet from third base. So we want to find d theta dt, how quickly theta is changing with respect to time. At the instant in time when the runner is 30 feet from third base, that means when x is 30. So we're looking to find d theta dt when x is 30. Now we have to come up with an equation that relates our variables. So our variables would be the x here from the rate that we know and the theta from the rate we're trying to find. So we need to come up with an equation that relates x and theta. Let's go back to our picture. I forgot to label theta, but let's go ahead and add that to our sketch here. That's the angle between the third baseline and the line of sight to the runner. So I'm looking for an equation that relates theta and x. So even though I drew a z in my diagram, I don't actually need that. I just need an equation that relates theta and x. And I have my 90, I have this right triangle. I can use possibly Pythagorean Theorem, but that's going to give me two unknown variables in my equation. Well, no, Pythagorean Theorem, I'd have to use the z. And we don't have any information about z. We don't know the rate of change of z. We don't know the value of z. So let's not even use the z. In fact, I'm going to take that out of our sketch. Let's use the theta and the x and the 90 since those are all important to this situation. So theta is an angle, and I have a right triangle, and I can use my trig definitions involving x, the opposite side, and 90, the adjacent side. So I know the tangent of theta is x over 90. And that equation, tan theta equals x over 90, relates my variables x and theta, which is what I want. So step 4, now that I have an equation relating my variables, I'm going to take the derivative of both sides using implicit differentiation. I'm taking the derivative with respect to time t. So the derivative of tan theta is secant squared theta if I'm taking the derivative with respect to theta, but I'm not. I'm taking the derivative with respect to t, so we need to adjust for that change in variable. Using chain rule, we're going to multiply by d theta dt. And that term turns our derivative with respect to theta into a derivative with respect to t. Okay, equals, and then I need the derivative of x over 90. Let's think of x over 90 as 1 over 90 times x. And then we can use our constant multiple rule. So the derivative of x over 90 is just 1 over 90, again, if I'm taking the derivative with respect to x, but I am not. I'm taking the derivative with respect to t, so I have to compensate by multiplying by dx dt. That converts my derivative with respect to x into a derivative with respect to t. And now we'll move on to step 5, where we substitute in all of our known values and solve for our unknown. We're trying to solve for d theta dt when x is 30. Let's go back to our picture. When x is 30, so at x equals 30, I have two legs of my triangle, the opposite leg 30, the adjacent leg 90. I can use the Pythagorean theorem to find the length of the hypotenuse. Now, I had that labeled as z and I erased it because I said we didn't need it, but actually we do need it here, and the reason for that is if we go back to our equation in number 4, it's asking us to find the secant of theta. And secant of theta involves the adjacent leg and the hypotenuse, so I do need to know the length of the hypotenuse here. So I'm going to use Pythagorean Theorem to solve for that hypotenuse. I know that the square root of leg squared plus leg squared is going to give me hypotenuse squared. Well, the square root of leg squared plus leg squared will give me hypotenuse. Okay, so that's the square root of 9,000, which is 30 times the square root of 10. So at x equals 30, z equals 30 times the square root of 10. And now we are ready to go back and substitute in the values into our equation. So what is the secant of theta? Well, the secant of theta is hypotenuse over adjacent. So the hypotenuse, 30 root 10, over the adjacent leg, 90, that's the secant of theta. We actually need the secant of theta squared times d theta dt, that's what we're trying to find, d theta dt, equals 1 over 90 times dx dt. And we know dx dt is negative 24. Okay, so to solve for d theta dt, and we can go to the calculator for this, we've got basically negative 24 over 90 divided by 30 root 10 over 90, all of that squared. And that gives me negative 0.24. Now our units are going to be the units for theta. Theta is our angle measured in radians, per our units for t, and our time t is measured in seconds. So our units are radians per second. Negative 0.24 radians per second. Number 11. Sand is being dumped off a conveyor belt onto a pile in such a way that the pile forms in the shape of a cone whose radius is always equal to its height. Assuming that the sand is being dumped at a rate of 10 cubic feet per minute, how fast is the height of the pile changing when there are 1,000 cubic feet on the pile? Step 1, we're going to draw a sketch, and we need to draw a cone whose radius is equal to its height. It doesn't have to be perfect, but there's basically our cone right there. The radius of the cone and the height have the same measurement, so I'm going to call both of those x. The radius and the height, both x. And we don't really have any constants. Let's see, nope, to label, so I think that's good for our sketch. We'll go on to step 2. We're going to write down the rate that we're given and the one we're trying to find. We're told that the sand is being dumped at a rate of 10 cubic feet per minute. And the cubic feet per minute is a clue as to what variable they're talking about. Cubic feet measures volume. So they're talking about the rate of change of volume with respect to time, cubic feet per minute. So I know that dV dt equals 10 cubic feet per minute. And since the volume is getting larger as sand is being dumped onto the pile, this is a positive rate. Now the one we're trying to find, let's see, how fast is the height of the pile changing when there are 1,000 cubic feet on the pile? So the height of the pile in my diagram is labeled as x. I want to find dx dt the instant when there are 1,000 cubic feet on the pile. Again, that's referring to the volume, when the volume equals 1,000. So now we need an equation. Step 3, we need to come up with an equation that relates v and x. What equation do we know that relates v and x? The volume and, well, in this case, x is the radius and it's the height. Well, let's start with the volume of a cone. The formula for volume of a cone, v equals 1/3 pi radius squared times height. Now we can rewrite this because in this particular problem, the radius and the height are both equal, and we've already labeled them as x. So our equation is v equals 1/3 pi x squared times x, or in other words, x cubed. So here's my equation that relates v and x. Step 4, I'm going to differentiate with respect to time t. The derivative of v is 1, but that's if it's with respect to v. If it's with respect to t, it'll be 1 times dv dt, or just dv dt. So the derivative of v with respect to time is dv dt, equals, now I need the derivative of 1/3 pi x cubed. 1/3 pi is a constant, so I'm going to use my constant multiplier rule. So 1/3 pi times the derivative of x cubed. And the derivative of x cubed is 3x squared with respect to x, but I need to take my derivative with respect to t, so I'm multiplying by dx dt to compensate for the change in variable. 3x squared is the derivative with respect to x. We multiply that by dx dt to get the derivative with respect to t. We can simplify here a little bit. I've got 1/3 times 3, that's just equal to 1. So dv dt equals pi x squared times dx dt. Now we want to substitute in all of our known values into this equation. We know that dv dt equals 10. And then we have pi times x squared. We have to figure out the value of x at this moment in time. When the volume is 1,000, what is x? Well, let's go back to our volume equation down here. When the volume is 1,000, we can solve for x. 1,000 equals 1/3 pi x cubed. Multiply both sides by 3. We get 3,000 equals pi x cubed. Divide both sides by pi. We get 3,000 over pi equals x cubed. And then take the cube root of both sides. We get the cube root of 3,000 over pi equal to x. So I'm going to come back up here and substitute that in for x. And it's fine to get a decimal value at this point, and you put the decimal value in for x. I'm just going to put it in here as is. So I have the cube root of 3,000 over pi. All of that has to get squared. And then times dx dt, which is what we are solving for. So dx dt equals 10 divided by pi times cube root 3,000 over pi squared. And that simplifies to 0.0328. And now let's think about units. The units for x are feet, and the units for t are minutes. So dx dt has units of feet per minute. So 0.0328 feet per minute. Number 12. A swimming pool is 60 feet long and 25 feet wide. Its depth varies uniformly from 3 feet at the shallow end to 15 feet at the deep end as shown below. Suppose the pool has been emptied and is now being filled with water at a rate of 800 cubic feet per minute. At what rate is the depth of the water, measured at the deepest point of the pool, increasing when it is 5 feet deep at that end? And over time, describe how the depth of the water will increase at an increasing rate, at a decreasing rate, or at a constant rate. So let's label our information. We already have the 60 feet length of the pool labeled, and it's 25 feet wide. The depth, which we can also label right here, is 3. So if I were to draw a horizontal line going across here, it's like I'm shaving off the top 3 feet. That's 3 feet here, and then the remaining 12 feet here. Now we have water filling up this pool. So we have a right triangle here inside of the larger right triangle. The depth of the water, I'm just going to call that y since it's a vertical distance, is this distance right here. And then we also have this horizontal distance of the water line. So I'm going to call that x. So I have this right triangle with legs x and y, and I have another right triangle with legs 60 and 12. So it might help if I draw this a little bit bigger over here. So I've shaved off the top 3 feet so that I get a right triangle rather than the trapezoid that it was. And then we have our water line here. So we have a similar right triangle. So this is x, this much here is y, and then we have this is 12, and this whole piece here is 60. Okay, so there's our sketch with our constants and variables labeled. Next, we want to write down the rate that we're given and the one that we're trying to find. So we're told that the pool is being filled at a rate of 800 cubic feet per minute. Cubic feet is describing volume. So this is dV dt. The rate of change of volume with respect to time is 800 cubic feet per minute. And since the volume is increasing, this derivative is positive. We are trying to find the rate that the depth of the water is increasing when it's 5 feet deep at that end. So we want to find dy dt when y equals 5. So now I can see the variables that I'm trying to relate are volume, v, and that depth of the water, y. So I need to come up with an equation that involves v and y. Well, let's find the volume of the water. So in this second sketch that I drew, it's only a cross section. It's just this 2D view. But the water in the pool obviously goes back. I just don't have room to draw it going back. But we can see up here that it goes back a depth of, maybe depth isn't the best word, but it goes back a length of 25 feet. So what we have, if you imagine the water itself filled in the bottom of the pool here, we have a right triangular prism. It's not sitting on its base, it's kind of turned sideways, but it is a right triangular prism. And the volume of a prism is just the area of the base times the height. So the area of the base is the area of the triangle, and the height of the prism would be the 25 feet. So my volume for this triangular prism is going to be 1/2 times x times y, that's the area of the triangle, times the 25 feet that it's going back. That's the volume. Now, problem here, we have 3 variables. So I'd rather not take the derivative of this equation right now because I'd have to use the product rule, and since I'm taking the derivative with respect to time, I'm going to have a dv dt, a dx dt, and a dy dt all in this equation. And we don't have any information about dx dt. So that's going to make it more difficult. I would like to try and eliminate that x because, again, if you look at step 2, the only 2 variables I'm interested in are the v and the y. I would like to eliminate the x before I take the derivative. I don't have to, but the derivative is going to be a lot more complicated if I leave that x in there. So how can we relate x and v or x and y? If I want to substitute the x out of the equation, I have to write it in terms of one of my other variables, either v or y. Well, we've got this small blue triangle here sitting inside of a larger triangle. So I can use the fact that these are similar triangles to set up a proportion. I know that the legs, the ratio of the legs in the smaller triangle will be the same as the ratio of the legs in the larger triangle since they are similar triangles. So I have the ratio x to y, so that's in my smaller triangle, long leg over short leg, is equal to the ratio of long leg over short leg in the larger triangle that it is similar to. And we can solve this, multiply both sides by 12, multiply both sides by y. So I'd get 12x equals 60y, and then divide both sides by 12, I get x equals 5y. So now I know that x is equal to 5y. I can substitute that into my equation for x. I can make that substitution now. So my volume equation then becomes 1/2 times 5y times y times 25. Now I only have the variables v and y. That's going to make my derivative a lot easier, but I still don't want to take the derivative just yet, or I'd have to use product rule. I want to simplify this as much as possible first. So let's multiply our two y's together, and then let's multiply our constant values together. Well, 5 times 25 is 125, and that's not evenly divisible by 2. So I think I'm going to just write it as 125 over 2, and then the y times y is y squared. And you'll see why I did that in a moment, because when we take the derivative, we're going to end up multiplying that coefficient by 2. So step 4, I want to take the derivative of both sides using implicit differentiation. We're finding our derivative with respect to time t. The derivative of v with respect to t is dv dt. The derivative of 125 over 2y squared, I'm going to use my constant multiplier rule and my power rule. So it'll be 125 over 2 times 2y, but that's the derivative with respect to y. Since we're taking the derivative with respect to t, we compensate by multiplying by dy dt. And now conveniently, these 2's cancel out, and I have dv dt equals 125y times dy dt. So step 5, we're going to substitute in all of our known values. I know that dv dt equals 800. And we have to find a value for y. Well, I know at this moment in time, y is equal to 5. That was given. And we're trying to solve for dy dt. So we divide both sides by 125 times 5. And we get dy dt is equal to 1.28. Now our units are going to be the units for y, and the units for y, the height of the water is feet, and the units for t, I think that was minutes. Yes, minutes. So our answer, the 1.28, has units of feet per minute. Number 13, a ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 3 feet per second. How fast is the top of the ladder moving down the wall when the base of the ladder is 7 feet from the wall? So first let's draw our sketch. We have our ground, our wall, and our ladder leaning up against the wall. The length of the ladder is 25 feet, so that's a constant. The length of the ladder is not going to change. What is going to change is the distance between the base of the ladder and the wall as we slide the ladder out away from the wall. And then also this distance here, the height between the ground and the top of the ladder, is going to change as the ladder slides down the wall. So we don't need that. Step 2, let's write down the rate that we're given and the one that we're trying to find. So we're told that the base of the ladder is pulled away from the wall at a rate of 3 feet per second. Pulled away from the wall. So we're describing x, that rate would be dx dt. As the ladder is pulled away from the wall, the distance x is actually getting larger, so this is a positive rate. So dx dt equals 3 feet per second. Now we're trying to find how fast is the top of the ladder moving down the wall. So we want to know how quickly y is changing with respect to time. We're going to find dy dt at the instant when the base of the ladder is 7 feet from the wall. That's describing x. So at the instant when x is equal to 7. Now what we need is an equation that relates our variable x and our variable y. And we can get that using Pythagorean Theorem. I have a right triangle here, so I know that x squared plus y squared equals 25. Now that I have my equation relating my two variables, I'm going to take the derivative with respect to t. The derivative of x squared is 2x with respect to x, and then times dx dt to get the derivative with respect to t. Plus, the derivative of y squared is 2y with respect to y times dy dt equals the derivative of 25 is 0. Now we want to substitute all of our known values into this equation. So I need to have a value for x to substitute in and a value for y. Well, we know that x equals 7 at this moment in time, and at the moment when x is 7, we can compute the value of y using Pythagorean Theorem. So we would do 25 squared equals leg squared plus leg squared, so 7 squared plus y squared. And then y squared equals the square root of 25 squared minus 7 squared, and we get y equals 24. So at the moment in time when x is 7, y is 24. And now substituting in our values, we have 2 times x is 7, times dx dt, that's 3, plus 2 times y, and at this moment y is 24, times dy dt equals 0, and we're solving for dy dt. So we get dy dt equals, if I subtract the 2 times 7 times 3, get negative 2 times 7 times 3 over, and then divide both sides by 2 times 24. And we've got our 2's cancel. 3 over 24 reduces to 1 over 8. So I get negative 7 over 8, which is negative 0.875. And our units, the units for y are feet, and the units for t, seconds. So our rate dy dt has units of feet per second. Part B, consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So it's that same instant in time, and because it's that same instant in time, we can use the rate that we found in part A if we need it. The dy dt equals negative 7 over 8. That's dy dt at the instant when x equals 7. But this time we're not trying to find dy dt, we're trying to find the rate of change of the area of the triangle. So we want to find dA dt, where A is the area of the triangle, at that same moment in time, at the instant when x equals 7. So now we need an equation that relates A with x or A with y, or both x and y, since we know both of those rates. When you write your related rates equation, you're using the variables that are involved in the rates that you're given and the rates that you are trying to find. So we know the area of a triangle is 1/2 base times height. So let's look at that. Area equals 1/2, the base is x, the height is y. Now it may seem like we have one too many variables. We do have 3 variables. However, I don't know dA dt, that's what I'm trying to find. And I know dy dt at this instant, and I know dx dt. So it's okay in this case that we have 3 variables. Let's go ahead and take our derivative. Unfortunately, we do have, since there are 3 variables here, we are going to have a dA dt, a dx dt, and a dy dt. We also have to use product rule to find this derivative. I'll use 1/2 x as my first factor, and then y as my second factor. So the derivative of a with respect to t is dA dt. Now the derivative of 1/2 times y, we're going to use product rule. So I take the derivative of 1/2 x, and that's 1/2 times dx dt. So that's derivative of the first, and now we multiply that times the second plus the first, 1/2 x, times the derivative of the second. Now I need the derivative of y. Well, the derivative of y is 1 times dy dt. And then we'll substitute in all of our known values. dA dt is what we're trying to find, so we'll leave that. 1/2 times dx dt is 3. I know that. Y at this moment in time, when x is 7, y is 24. We found that in part A. Plus 1/2 times x is 7 at this moment in time, times dy dt, and we can use that answer from part A. We found dy dt when x was 7 as -7/8. So we simplify this, and we get dA dt equals 32.938. Now our units here are the units for A, the area of the triangle. These legs are measured in feet, so the area is square feet. And then the time t is measured in seconds. So our rate, dA dt, is 32.938 square feet per second, or feet squared per second. Part C, find the rate at which the angle formed by the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. So in our diagram, theta is this angle up here. It's the angle formed by the ladder and the wall. And we want to find how quickly that angle is changing when x equals 7. So find d theta dt when x equals 7. So now I need to write an equation that relates my variables. I need to involve theta and x, or theta and y, or theta and x and y. Since I know dx dt and I know dy dt at this moment in time, it's okay to have x's and y's in my equation. But I can do this without all three. So I've got my angle theta, the opposite side is x, and the hypotenuse is 25. So I can say sine of theta equals x, that's the opposite side, over 25. The 25 is a constant. So here is an equation relating theta and x, and now I will take the derivative with respect to t. The derivative of sine theta is cosine theta if I'm taking the derivative with respect to theta, but I'm not. I'm taking the derivative with respect to t, so we have to multiply that by d theta dt. Equals, and then the derivative of x over 25, think of that as 1 over 25 times x, so it'll be 1 over 25 times dx dt. And now we're going to substitute in our known values. The cosine of theta will be the adjacent leg over the hypotenuse, so 24 over 25, times d theta dt equals 1 over 25 times dx dt, and I know dx dt is 3. Okay, so I can simplify this a little. I can multiply both sides by 25. That'll get rid of my 25s. And then I have d theta dt equals 3 over 24, or 1 over 8. And now my units will be units for theta. Theta is measured in radians. And then units for t. T is measured in seconds. So my rate, d theta dt, is 1/8 radians per second.